Okay, so hi everyone. Thank you for the kind invitation. And of course, it'd be much nicer if we could be physically present in Bangalore and discuss in person, but it's nice that we can update each other online this way. So today I'm going to talk about how the idea of macroscopic fluctuation theory possibly could work for studying large deviation properties in integrable systems. So this theory, macroscopic fluctuation theory, has been developed for, I don't know, like 20 years, and it has primarily been applied to classical diffusive systems. But the underlying idea seems to be rather universal. So I think it's a natural idea to try to apply this MFT to study some large deviation properties of transport. I mean, in particular, quantum transporting integrable systems. So this is based on my ongoing collaboration with Benjamin Doyle and Tomohiro Sasamoto. And I'm not going to say we understood the full picture, but rather I'm going to just give you some kind of status report of this project. Okay. Oops. So before giving you some theoretical aspect of it, let me just remind you of how large deviation or full counting statistics, if you wish, has been actually experimentally studied in the past decades. So full counting statistics, which is about the statistics of transport, like not only about the average current, but including variant, the second cumulant noise, if you like, third cumulant, and all these higher cumulants associated to transport have been studied experimentally, and particularly in the context of electron transport. For example, if you look at this kind of cartoon, it's very simple. Just some voltage is imposed on this macroscopic system, and there is current running through the resistor, and you could monitor the current as well as its noise from this ammeter. So you could really read off these two physically relevant observables from this kind of very simple experiment. Of course, you could do a little more elaborate experiment and measure, for example, the skewness, third cumulant, as well as try to see if this fluctuation theorem, which is a theorem that is telling us that there's a particular relation between probability of entropy increasing events and the probability of entropy decreasing events. So there is a theorem about it, and then experimentally it was also verified in some cases. Also, it's kind of interesting to note that there was a measurement of the shot noise like 20 years ago, and this led to the confirmation of the existence of fractional charges. So it's really not just theoretical. The study of full counting statistics, not just theoretically motivated, but it's really experimentally accessible. More interestingly, recently, this full counting statistics of the many-body assessment quantum many-body systems has been also applied to spin transport using ultra-cold experiments. For example, in this very recent experiment, I think Joel and Mao were briefly mentioning about this as well. In this experiment, what they did is to study full counting statistics of spin transport in the isotopic spin chain by loading some bosonic rubidium atoms in 2D optical lattice. And the upshot of this experiment was that they could really take a snapshot of the entire sample at each time instant. So by just collecting all these snapshots, they could recreate the probability distribution of the spin transport. And from that, they could see that the fluctuation of this spin transport is actually governed by some random matrix process called Gaussian orthogonal ensemble, provided that the system is initially in a weakly polarized state. So it's really this study of Fluctuating statics is started from electron transport and spin transport, and it's really becoming, the importance of it is really increasing, I think. So I'd say now this a versatile tool to study Fluctuating statistics in quantum many-body systems, in particular in integrable systems, really highly desired now. Okay, so maybe this is not really necessary, but anyway, I made this slide. So let me just remind you of how the basics of large deviation theory. So large deviation theory, at least in classical cases, is primarily concerned with the rare fluctuation of some fluctuating quantity, IT, that is extensive in T. I mean, this parameter could be whatever you like, but generally it's time. It's in the context of transport. So said in another way, this theory is caring about the probability distribution of observing some AT that is significantly deviating from its average value. So what we have to do in this theory is to try to, compute this probability distribution. And of course, this probability distribution has to have a peak, the most likely value, because that's most likely. So as I said, AT could be arbitrary, but generally you take it as a time integrated current. Yeah, in many cases, not all the cases, but in many cases, associated to some charge. And this time integrated current that is evaluated at x equals 0 could also be written as the difference of total charges in the right half system. So now this large deviation theory asserts that for large t, the probability should go like this, so decaying exponentially in t, where its coefficient is called the large deviation function. And because the probability of observing the average current is most likely, is naturally this large deviation function should hit its bottom. I mean, the minimum value of it should be reached when j is taken as its average, when I becomes basically 0. So this probability distribution basically encodes all the statistics of transport, but in practice, it's not that easy to work with this probability distribution directly, but rather it's always often easier to work with the thing called generating function, which is defined in this way. And this scaled Cumulus generating function, f of lambda, is related to the large deviation function in this very simple way. I mean, Legendre transform essentially. So they are kind of changeable if you wish. So what I'm going to do is to try to compute this f of lambda, as well as it's a Taylor expansion coefficient called cumulus. Okay, in the quantum case, which is the case I'm primarily interested in, the notion of fluctuating variable becomes kind of less clear, and also JT is not really a natural observable because it's integrated over the time, and it's not a local observable. But still, you could sensibly define something like this. I mean, this kind of probability distribution by measuring the total charge Q0 at time 0 and Qt at time t/t in the right half of the system. So by the difference of these guys, Qt and Q0 is essentially the total charge is transferred across x equals 0 during this time. So you can write down the probability distribution as a function of the difference of Qt and Q0, and that would be basically the equivalent of this probability distribution. In any case, you can have this kind of f of lambda or probability distribution, I mean, large deviation function in both cases. And you could also it's a common practice to define also cumulants like this, because directly calculating f from lambda is not that, I mean, could be hard. So, but in many cases, calculating some lower, I mean, some lower cumulants like second or third or fourth cumulants is more amenable. So that's what people do. Okay, so just let me quickly mention that in quantum cases, there are a number of spectacular results, theoretical results in the study of full condensed statistics. Of course, I'm not saying that in the classical cases there are not as many interesting results as in the quantum case. I'm not saying that. I'm just explaining quantum case because that's the cases I'm interested in. For example, the prominent example is the celebrated Levita philosophic formula, which is exact scaled conjunction function for charge transport for free fermions. This is available, and it's very versatile, and it works even in the presence of impurities. There are also known exact cases, like even in interacting cases, like integrable quantum impurity systems, like Anderson model, interacting resonance level model, conformal field theories, both in 2 dimensions and higher dimensions. And okay, this isn't really interacting, but the quantum harmonic chain is also important. Example, I mean, it's free system, it's important. And also interacting integrable systems. So in fact, this exact f from lambda as well as cumulants are available in interacting systems. So what I'm going to do is not really trying to get something new, but rather trying to produce all these results that were obtained before, with the hope that kind of expanding the horizon of MFT. I mean, it's not, we know that it's quite universal, but it's really maybe even more universal than we expected. So that's kind of idea. Okay. So finally, I can talk about conventional macroscopic fluctuation theory. So it's also called hydrodynamic activation theory because the only inputs needed for this theory to work are some transport quantities like diffusion constants or mobility. So it's quite universal. I mean, essentially all you need to know is hydrodynamics of the model. Then you can do also this MFT. And that's it for the beginning. It has been really developed for mainly for diffusive systems, but the idea is universal, as I explain now. So what does it say? So let's consider the probability of observing some hydrodynamic density and current profile like this during a time t, hydrodynamically large time t. MFT then claims that for diffusive systems in definite volume, of course you can think of some finite volume case, but indefinite volume case here, probability of observing these profiles should go like this with this large differential function provided like this, where JDiff is fixed law. It's a hydrodynamic current in the diffusive case, where these is diffusion constant, nonlinear diffusion constant, and the sigma rho is mobility. So this is if you know a bit about MFT, should be familiar. But for those who are not really, who don't know really much about MFT, maybe this is kind of I don't know, where does it come from? It's like coming out of a hat. So I'm going to give you one justification. There are some ways of justifying this assertion, but in any case, let's take it as a given fact and let me write down the probability. No, sorry, scaled commutative function of some charge. Okay, for simplicity, I'm considering some single component case, but of course you can generalize to the multi-component cases as well. The scaled commutative function is like this, where path integral is performed over all the space-time trajectories and with respect to rho and j. And if the initial condition is fluctuating, which is usually the case, then you also have to put the probability of finding such initial density profile here as well. And because this is hydrodynamic theory, continuity equation is supposed to be satisfied at each space-time. So just to ensure that it is satisfied all the time, you put theta function in here. And then finally, you also have to put the probability of finding such profiles, which are to be integrated over all the trajectories. That's the formula, at least formally. So let me start with this probability of finding the initial density profile. So like I said, it's obviously 0 if there's no fluctuation initially. But in general, you have it, so you got to compute it. To compute this, let's consider, for example, some simple case like, let's say you have a system of size L containing large n particles, and then the probability of finding n particles, small n particles in a small but still large enough volume small L at the position x is given by in this way. I mean, this can be very simply computed statistically mechanically by just, calculating the number of ways of allocating small n particles in this small volume L. You can do it. And at the end of the day, for under the limit where both small L and large n are large, but the ratio of it is small because large L is much larger, suppose, compared to small L, you get this kind of large deviation function, where f of rho is just a free energy as a function of density, and here rho star is a homogeneous background, a density of the homogeneous background. And if you can also expand this when rho and rho star are close to each other, their expansion, and you can get this kind of thing, where I used the local instant relation in passing from the second expression to third expression. And this is kind of similar to this assertion. But yeah, this is nothing more than just analogy. So let me give you some more solid justification. So you can generalize this argument to the continuum case. I mean, not just to these bunch of particles, even infinite number of particles. Like you have initially the system that is in the local equilibrium with this given distribution, and then you can think of the probability of finding a particular distribution, rho of x and 0, that is deviating from this initial equilibrium, local equilibrium state. And this is just a simple generalization of these considerations. So I'm gonna just write down the final result, and actually it's neatly given by relative entropy. But for later use, I'm gonna write it in terms of entropy density, free energy density, and Lagrange multiplier defined in this way. Now you can interpret MFT predictions based on fluctuating hydrodynamics. So what fluctuating hydrodynamics says is that the macroscopic dynamics of some many-body systems should be governed by the Langevin equations, not only these diffusive equations or the Stokes equation, but you also have to put the noise just to ensure dissipation fluctuation relation. But morally speaking, why this noise is here is because when you do derivative expansion in hydrodynamics to obtain diffusive correction like Jacopo did in the first state, you neglect basic high order derivative expansions because these are infrared process, and that doesn't basically play any role in this low energy effective dynamics, which is hydrodynamics. But they might do something in some particular situations, and the idea of fluctuating hydrodynamics is to put all the non-trivial contribution that possibly coming from these neglected contributions into this white noise. So of course this phenomenology, but as you probably know, it has been so very successfully applied to many systems, so long as it's not super diffusive. So we use this fluctuating hydrodynamics, and then we can show that this chaotic command generating function that I wrote down in here is equivalent to this expression, which I think is simpler because all we got to do now here is to integrate it over all the possible density profile in this space-time, and then take averaging over the noise, which is just taking account for the effect of fluctuation. So this is, if you believe in fluctuating hydrodynamics, this is what is being done here is taking care of correct fluctuation that is generated during the dynamics. And because this is the same as the previous one, so what you can conclude from this is this MFT prediction on this probability distribution really reproduces the correct fluctuation. So this is, I think, one way of justifying it, but there are some other ways too. What I'm saying here is, my point here is I'm gonna take this as a kind of MFT basic equation, and I'm gonna play with this and try to calculate something rather than the initial formulation of a scaled homogeneous function. Okay, so but what I'm interested in here is not actually diffusive systems, but the system that supports ballistic transport or hyperbolic systems, if you wish. For instance, you can consider the Hydro equation for the TIFR. Yes.
Ask a question.
Of course.
Oh, in your previous slide, where you have previous slide, yes, yeah. So here you have according to FHD. So you have defined the Langevin equation for the fluctuating observables, but there should be a L dependence in the strength of the noise according to macroscopic fluctuation theory. Otherwise, the integration we couldn't do the integration because the saddle point L is important to calculate the saddle point of the integration that you defined below.
Yes.
So,
so yeah. So you're saying independent of the noise?
Sorry?
We're talking about the independence of noise. What are you saying about the noise?
I'm saying that there should be an sigma rho by L that is in general predicted by MFT.
You should. You mean I should divide this by L?
Yeah. Yeah.
Okay. Yes, I think in some formulations you should do, but I'm considering here an infinite volume case because that's what I'm going to care about. So I'm not sure in that case. I mean, of course, we take a large element here that go away. So maybe you can take appropriate scaling again to ensure that even taking a larger limit, there is some finite noise, but I think it's a matter of scaling, really. Should put a L here in this formulation. Essentially, take a larger limit. But in some formulations, they don't really put a larger limit, like directly considering the infinite volume case from the beginning, and then they could just write down this equation, right?
Okay, so you're saying that the appropriate scaling will take care of the effect. Okay.
Yes, I think so. By just rescaling this equation.
Okay, thanks.
No problem. Okay, so let me proceed.
You are treating eta as a simple noise, right?
I'm sorry.
Is eta is treated as a simple noise, right? Or is it a multiplicative noise? When you take
it's a white noise,
which is the noise.
Yes, it's a white noise. Yes.
But the way it is appearing in the equation, it's looking like a multiple noise, right? So you treat eta as a simple noise.
Yeah, the role of the noise here is really a macroscopic noise coming from thermal fluctuation.
I know the
it's
origin.
From,
I'm not asking the origin, but are you treating it like a simple noise or a multiplicative noise?
I'm not sure what you mean by simple noise, but
Okay,
it's not magnetic noise.
Okay, don't worry.
I think it's a multiplicative noise, and also it's a conservative noise. So I think you're missing a derivative there in the noise.
Ah, yes, true. Yes, you should put the noise in here because the noise is supposed to be in this current. So yeah, yes, you're right. Thanks for pointing out. It's there should
And
be a derivative here.
if sigma is non-trivial function of rho, then it's a multiplicative noise. So yeah.
Okay, okay. Thank you.
Then there are a lot of other complications. Whether you want to take Ito interpretation or Stratonomic interpretation.
Okay.
Anyway, go ahead. Yes.
Yeah. So, okay. Let me just proceed. So, okay, yeah, this noise, origin of noise, and yeah, it was a bit soapy, but it should be. I mean, at the end of the day, I don't really even consider noise because I'm going to take scaling. I mean, the Euler scale limit, as you can see from the next noise. So, I'm just trying to say that here is a MFT formulation for the diffusive systems, and if you take a Euler scale limit of it, I mean, not Euler scale limit, but trying to ignore the effect of noise coming from the dynamics, because in the ballistic case, you don't really have to consider the fluctuation coming from noise, but the fluctuation is coming from just initial condition only. Things get substantially simpler because this is the scaled command generating function that you can play with. So again, I'm considering the single component case, and this looks less harmful than the previous one because there's no noise. And okay, anyways, this is as I take it as a defining MFT prediction for the scaled command changing function. And then you can write down a bit more elaborate expression of it by exponentiating this data function here. So this new variable h, auxiliary variable, is introduced, and as a result, you get the MFT action like this. So this is what I call the MFT action. Okay, and it's easy to see that this action is dominated. I mean, it's going to scale like a linear in T for large T. So if you take a large T limit in this path integral, all the most dominant contribution is, of course, coming from the saddle point of the MFT action. So now problem was down to do the optimization problem, like in the diffusive.
Excuse me, where it has gone in your last equation?
I'm sorry?
So in the bottom of the slide, you have expression of S, where H is. In the right-hand side, where do you have H?
Yeah, Takato, you forgot to put H.
Oh, sorry. Yeah, this is here should be H in here. I'm sorry. Sorry. In the inside of the integral, so there should be H of x and t here.
Good.
Sorry about that. Yeah. Let me just reiterate. Here should be H of x and t. Okay. Yeah. Otherwise, it doesn't make sense to be H dependent here. In any case, you can do an optimization problem and get this kind of set of MFT equation. Here, just to say that this flux Jacobian is it is controlling the strength of the Ballistic transport, which is defined in this way. The time evolution of this MFT equation is basically the same as the Hydro equation, but the boundary condition is now incorporating the effect of bias in the dynamics. So this dynamics is different from, of course, different from hydrodynamics, but rather it's a dynamics that is making the refluctuation more typical. That's a kind of loose interpretation of it, I would say. But the situation here is a bit subtle compared to the diffusive case because, as you probably know, this kind of linear equation, the equation that is non-linear in the density, is often plugged by some singular behavior, which is called shocks. So you have to deal with it. But if the situation is even worse because there's no lux condition or entropy condition that you can rely on to single out weak solution from this equation. So it's hard to analyze. One way to get around though is to start with MFT, with the diffusive corrections, and consider some order limit. For example, this was done by in the case of TSEP and the WSEP. I mean, WSEP is it's called the weakest. It stands for a weakly asymmetric simple exclusion process. And if you take a totally asymmetric limit of it, you can get a totally asymmetric simple exclusion process. But the situation in the integrable case could be a bit better because actually there's no shock in the GHD, and the only solutions to the Riemann problem, or in general initial condition problem, is contact discontinuity. So it's like entropy. Sorry, it's a shock without entropy production, if you like. So you don't have to worry about this present shock. So it could be better, and it turns out that it is indeed more analytically amenable. Okay. I might run out of time, so let me just skip this. Just to say that there is a formalism called Jensen-Vardan formalism for the transport in TISEP, but it's not really relevant, directly relevant here. So now comes to generalized hydrodynamics. So I think there are a number of talks about GHD already, and it's not really necessary to really provide you an introductory explanation to it. So let me just say that in integrable systems, thermodynamics as well as the dynamics of the system are dictated by the scattering data, which is particle species in this Persian relation and the two-body asymmetrics. Just for brevity, of course, I'm going to consider the simplest case, which is an integral system with a single species with a diagonal scattering, scattering and defined on the line. So this is a simple case. Of course, you can think of the Linear model or Cinci-Gordon model if you want some concrete examples. But the idea should be easy to generalize to the more convoluted situations. But there is a kind of underlying principle I want to emphasize in GHD, which is that there is a universal kinetic intuition behind it, which is that on a hydrodynamic scale, quasi-particles in integral systems behave pretty much like tracer particles of hadrods. For instance, you can think of tracer particles. So the tracer particles are like particles that are sitting in the middle of each rod. And so these bunch of black dots and are tracer particles, hadrods, and upon the collision, they just jump to the colliding rod and keep propagating with the previous at the same velocity. And this is basically what is happening for any integral systems as long as it's beta solvable. I mean, of course, this jump distance could be dependent on the velocity, but I mean, the basic principle is the same. So this is why GHD is so universal. And that would also motivate us to expect that MFT for integral systems should also be universal, because the only input needed for that is hydrodynamics of it. Also, just to know that there are a number of exact results are available in GHD because of the underlying integrity structure. So if you want to know about this, you can see these reviews. So for later use, let me just write down GHD equation in this particular way, where this A matrix is the same old Jacobian matrix, flux matrix. In the single component case, it's just a function, but now it's a matrix. There's actually another set of useful fluid variables called Lagrange multipliers beta theta, beta to the theta, which is following this kind of another kind of GHD equation. And beta is now defined in this way, where this C is susceptibility matrix, and it's satisfying this kind of relation between A. Okay, but there is also another third kind of a way of writing down GHD equation in terms of the normal mode, and you can choose really any normal modes you like, so long as they are transported in this convected fashion. So I'm going just to pick this particular normal mode, which is the pseudo energy, because this is going to be useful variable later. We can, usually people use, for example, occupation number, which is made out of this pseudo energy as well. So pseudo energy is more speaking, it's like quasi-particle energy in the presence of interaction. So I'm not really writing down its definition, but because it's not relevant. But it suffices to note that it's there's a transformation relation between beta and epsilon like this. So where R is diagonalizing the flux matrix in this way, with the effective velocities being the eigenvalues of A. So like I said, one of the crucial properties of the GHD is that its solution is neither shocks or a function. Usually it's just contact is continuity. So this would give us a hope that things could work. Okay, so, but to do that, to proceed, I have to remind you of how the initial value problems in GHD can be studied. So to motivate it, I think it's illustrative to kind of remind you of the same old initial value problems in a simple hyperbolic system case, which is like, I mean, like a Vargas equation, if you like. So here I'm considering Vargas-like equation where V of rho is just an arbitrary function of rho with this initial condition. And to get the solution of it, what you do is is called the method of characteristics. So you pick some position x equals u, and let's say you draw a characteristic curve from this point. I mean, and let's say this point is reached at a time equals 0. And you draw the characteristic curve in such a way that along that curve, rho is always constant. So this kind of equation is expected to be satisfied. And then if you define x in this way, then it's immediate to see that rho is indeed constant along that characteristic curve. And also importantly, there is the characteristic curve is always straight. In this simple case, by you can check it very easily. So now you can solve this characteristic equation of characteristics by invoking the fact that rho is transported in a very simple way along this characteristic line, and you end up with this kind of equation. And here a u is it's just an initial point, so you can draw this kind of bunch of characteristic lines for any arbitrary position u. But you can also change the point of view by saying that you pick some spacetime initially, and then try to draw the characteristic line so that rho is constant along that, and then you parameterize the point when that is reached when t equals 0 as a function of x and t. So you have x and t, and this is, you can do that by solving this consistently. Then what you get is that this solution to the method. the method of characteristics. So rho of x and t is given this way, in a very simple way, where u solves this equation. And essentially, we want to do the same for GHD. Now, the natural generalization is to write down this kind of equation, which immediately implies this relation. But the difference from the previous case is that the characteristic curve is not straight in this case, because this epsilon, the pseudo energy, is not just a function of x, but no, sorry, it's effective velocity. Effective velocity is not really a function of epsilon, but it's a functional of it. This makes this second derivative of x non-straight and non-zero, which means that the characteristic curves are not straight. But still, it doesn't change the fact that along the characteristic curve, epsilon is satisfying this kind of relation. So as in the previous case, you could try to parameterize initial point u and x in this way. And this is a kind of defining relation of u for the initial value problems in GHD. So the now question is, how do we determine this u, theta, x, and t? And clearly, this characteristic curves being non-straight isn't helping the situation. It turns out that you can get around in a simple way, well, not maybe straight, as simple, but there's a way, which is to change the coordinate. So now, of course, this is a coordinate. This coordinate system is x and t, but now you can map this x coordinate to the q, the new coordinate, with a state-dependent coordinate change. So this epsilon hat of q, t is expected to be the same as epsilon theta. So q is defined q is defined in this way. Firstly, it's so it's a really state-dependent coordinate, depending all these x and t and theta, where k is simply addressed p prime, and the addressing operation is as per usual. So I think people introduced this notion before. So with this q, epsilon hat is defined in such a way that if q theta is plugged in here, then it produces epsilon theta in this way. And then this epsilon q is epsilon hat q and t can be shown to satisfy this kind of free transport equation. So this transport velocity is not really t dependent anymore, but it's really a constant velocity. So because the particles are now transported according to this new transport equation, GHD equation, freely, but not on the same space-time coordinate as before, but now with the state-dependent phase space equipped with this kind of metric. So this is a new kind of point, and but still, this is a great news because you can solve this equation trivially because it's free transport equation in this way. And by combining a bunch of these definitions, like u theta is, I mean, by definition, this satisfies this kind of a relation, and also q theta was, epsilon hat was defined in this way using q theta. You immediately end up with this kind of relation from which you can infer that u theta has to satisfy this kind of equation.
Sorry, Takato, we have question from chat.
Yeah.
Ohad Spriban.
Yes.
Can you ask directly, Ohad?
Yes. So I must have missed it somewhere, but in the exclusion process, usually when we look from afar, there is a term that is proportional to the density 1 minus the density, so that the density does not, it's restricted between 0 and 1, right? So I missed it. Where is it hiding? Or can we see it in these equations?
Density here. Oops. So I'm dealing with, so actually I'm not really dealing with the density, but I'm dealing with energy. So here, so it doesn't have to be restricted to in between 0 and 1. But of course, other quasi-particle densities like, can I go back? In these guys are, I mean, it's easy to see that these guys are, I mean, it is by definition, this is quasi-particle density, so they must be in between 0 and 1, and you can easily see that. But just to let you know that epsilon doesn't have to be restricted to the kind of domain.
Yeah, sure. Okay, after the transformation. But here you say that from the A's we can see that.
You mean we can? What do you mean? Do you see what?
So at some point I would like to see that okay, so there are a few transformations which I have to look at closely and slowly, but somehow I would like to keep some intuition here. So at some point the results they should depend on you know, rho 1 minus rho when you are looking at large deviations or whatever you want to look at, right?
I mean, maybe it's.
Can I just add? So the rho 1 minus rho would be J. What Takato write as J? That's rho 1 minus rho intercept. So somehow you have to put it there.
In the case, intercept case, yeah. So yeah, but in general, it's in the GHD case, it's a non-trivial functional.
Yeah, sure. Okay. Okay, thank you.
Okay, so where were I? Oh, sorry. So yeah, in terms of new coordinate, these characteristic curves are straight. I mean, it's clearly it's straight, and also this relation should really be compared against this kind of equation that is defined U in the case of simple hyperbolic system. But in here, it's a new coordinate that is to be remembered. And also, this velocity here is really always constant. I mean, this velocity is always the same for any characteristic line. So long as theta is fixed. So this is kind of pointing to the fact that there's no shock in GHD, because shocks could be diagnosed by alignment of the bunch of characteristic lines, and that cannot occur in here because they are always parallel each other. But after being said all these, maybe you don't really have to understand this derivation, but the only thing you need to know is that there is a way to solve the initial value problem in GHD, and all you have to do is to define U theta of x and t through this kind of integral equation, and you plug that in here, and you get the initial, the solution for a variety of initial conditions. And of course, you can do the same thing when another kind of boundary condition, let's say t equals large t is provided. We can do the same thing, where r theta is defined in this way. Okay, so probably I should go quickly from here. Okay, good. MFT equation here is not correct because I've put the h here, so sorry about the previous mistake. Anyways, in the GHD case, there are a bunch of conservation laws. You can think of some transport associated to the physical charge, but you might as well also do to study large deviation associated to charge labeled by causal momentum, because these are also legitimate conservation conserved quantities, extensive, and they constitute a complete set of charges. So and that would make calculations slightly simpler, so I'm going to do it. But just to let you know that once you have scaled cumulative function, all cumulative things I'm going to compute, you can reproduce those of associated to physical charge immediately. Okay, so these are again MFT equations to be optimized, and these are a bunch of MFT equations. But directly dealing with this kind of equations is not really actually feasible. So what you have to do really is to introduce normal modes and that is why I was introducing the solution of method characteristics. For beta, we know how to transform and get the epsilon. You just have to do this kind of transformation. So motivated by this, you can also define new variable g in this way. A priori, it's not obvious if such a g could exist at all, but thanks to this kind of compatibility condition that is satisfied in integrable systems, you can have this kind of g sensibly. So combining this, you can write down a new set of MFT equations in terms of normal modes. And this is now easier to handle. To calculate f from lambda and the scaled cumulative function and the cumulant, you have to know how epsilon theta varies, because that is going to be needed for the computations. And to this end, of course, you calculate the lambda derivative of epsilon. And for simplicity, let's consider a homogeneous case. Of course, you can think of step initial conditional case, but or some other more complicated cases. But for simplicity, let's focus on the homogeneous case. Then you get that after some manipulations, this kind of relation. Yeah, maybe this is not really intuitively clear, but it's just that this is total derivative apparently. In the right-hand side, you can integrate over lambda and you get this kind of expression. And this can be used to calculate cumulants, lower cumulants at least, where just to recap that the cumulants are given in this way. I mean, just the Taylor expansion coefficient of the f of lambda. Okay, I'm going to just go through quickly because it's just technicalities. And once you have this equation for the epsilon theta, it's just a matter of going through elaborate Theta's computations. So it's trivial to produce, for example, C1, because it's by definition this is trivial. But I'd say C2, which is the second cumulant, is less trivial to compute. To do that, I have to know how rho instead of epsilon varies as lambda changes, and its value when and then the value of the derivative of it when lambda is sent to 0, which is given this way. And then using this, you can. Sorry, just also just for notation, this psi is what I call quasi-particle susceptibility. So, and this is defined in this by this kind of relation. So using this, you can compute C2, which looks like this, which actually has been computed in two ways. First one by biasing the dynamics, and also by another method that Benjamin called the ballistic fluctuation theory. But still, it's good to know that this MFT produces exactly the same second cumulant. Much less non-trivial, I'd say, is the fact that even third cumulant is agreeing with the previously obtained third cumulant that was also obtained by work by Benjamin, Jason Meyers, and Joe Bassier, and Rosemary Harris. So I couldn't bore you with the computation, just this is the final result, which is not that, it doesn't look so pleasant, I mean, a bit complicated, but this is really the same as the one obtained before. You can, in principle, could go further, calculate fourth and fifth cumulants if you really want to do that kind of computation, but I'd say this confirmation up to here should really be sufficient. And as I said, if you want to know the cumulants associated for physical charge, you just need to replace R inverse T with this H test. And just to further provide you a compelling evidence that these are all correct, some numerical check was performed in this work against hydrodynamics. So these are the cumulants for the energy, scaled energy, and agreements are, I think, unquestionable. So I'd say MFT is really correctly producing the large deviation properties of GHD. And you can also produce easily this Levitov-Letovic formula, for example, this pre-Fermi case, just a very immediate. So now question is, what is really the dynamics described by the epsilon theta? So as I said at the beginning, it's morally speaking, this epsilon theta, or in general, the solution of MFT equations are characterizing the dynamics where real fluctuations in the original dynamics becomes typical. So what kind of dynamics is really contributing to this atypical fluctuation? That is what this dynamics and MFT dynamics is telling us about. To understand something about it, you might it might be nice to try to compare with another approach, the ballistic fluctuation theory that Benjamin was briefly explaining yesterday. So the idea of the theory is to bias in the measure in this particular way by inserting this time integrated current, I mean exponential bit in this way. And if you do that, you can show this the fact that scaled cumulative function is just given simply by the current with respect to this new measure. And it turns out that this biased measure is homogeneous, stationary, and clustering. And therefore, you can sensibly define beta lambda of lambda associated to this kind of new measure. And of course, this in turn induces a flow of beta lambda in this way. And you can compute a flow equation of beta lambda. I'm not writing down how you can get it, but you can obtain a flow equation of it. And equivalently, you can also write down flow equation for epsilon lambda in this way. So having this kind of beta lambda, there seems to be a nice flow equation to satisfy this epsilon lambda. And essentially, if you have this, you can calculate the cumulants and scaled cumulative function, because this is basically saying that all you need to know to calculate the statistics of transfer charge at equals 0 is really information coming from the x equals 0, or just some vicinity of x equals 0. Now the question is, could we identify epsilon lambda with this epsilon 0 and t, which is coming from MFT? And why do I ask this question? Because they behave pretty much in a similar way. So to see this, we first notice that the dynamics described by MFT at x equals 0 is stationary, expected at these two boundary points, namely this house. And you can see this perturbatively lambda. When you try to compute the cumulant, you just take a multiple lambda derivatives and then take a lambda to 0 limit. And you immediately see that only terms under this limit with t dependence are these guys, which are clearly t dependent because t is in between these two values. So by order and order, you can show these things, hence this fact that the epsilon is stationary in the back of the time domain. And because dynamics is stationary at x equals 0 at all times, we can define a set of Lagrangian multipliers in this way and parameterize the stationary state. And also, you can, within the MFT, have this kind of relation. So this really motivates that this new beta lambda, I'm sorry for the notation, maybe I should have changed, but anyways, this beta theta 0 and t could be identified with this beta lambda used in the BFT. But there is a caveat, which is that it is highly non-trivial to show the stationarity of this epsilon non-perturbatively, because there are some subtleties, and in fact, there's no reason to expect that this is true away from the vicinity of lambda equals 0, essentially because you need this kind of stationarity just to ensure that the clustering of correlation functions and clustering in time is satisfied at x equals 0. So for the sake of having the the cumulants that are not blowing up, you need to, it was assumed and also shown that the stationarity of dynamics is satisfied in DFT, and you can also show this here, but just to say that it's not really necessary to have this non-perturbativity. I mean, you need to really show that the only vicinity of a lambda equals 0. And indeed, if you take lambda equals 0, then you can show that this, yeah, flow equation, it's really the same as flow equation satisfy this epsilon lambda from BFT. And I expect that this is still true for the vicinity of lambda, I mean, so long as lambda is sufficiently small. So this really kind of provides a nice comparison between the ballistic fluctuation theory and MFT. Okay, so how much do I have? How much time do I have? So when did I start?
Already
10 minutes.
Discussion
Yeah,
session.
I know. Yes, I know. So yeah, I'm gonna just yeah. Fluctuation theorem can be shown actually within the framework of MFT without invoking integrability, but clearly there is no time, so I'm going to skip all this. So there are some open questions that are estimated from this discovery. Just let me tell you one of them, which is that MFT, as in its current form, it's not really, doesn't seem possible that we can incorporate the effect of quantum fluctuations. That seems to really changes the derivation properties transport as was discovered in this work. So it would be nice to have extend the machinery of MFT to incorporate these quantum fluctuations, but that seems to be a bit going beyond the conventional MFT. So that'll be a future work. So okay, let's stop here, and thank you very much for your attention.
Yes, thank you very much, Takato. Thank you very much for a nice talk. So now, are there any questions or comments? If you have a question, raise your hand. Okay, Nahu?
Yes, so my question is basically, so you said that in GHD there are no shocks, right? So what guarantees that there are no shocks, and does the statement apply for any initial condition?
Good question. So the absence of shock is basically diagnosed by the fact that there is a particular condition satisfied with GHD or in general integrable systems called linear degeneracy. So normal mode of GHD is does not really depend on, I mean, the velocity of the normal mode doesn't depend on the normal mode of itself. So this is a kind of condition satisfied in the integral system, and doesn't matter what initial condition used. And this guarantees that basically, even if so the continuous discontinuity is basically the merger of the shocks and their function webs. So you could really see that within GHD because of this linear degeneracy.
Okay, thank you.
Jacopo, please.
Yes, hi.
Hi, Jacopo.
So, but if I understand correctly, so the main power of MFT is that just knowing what's the average of the current, you can access all the moments, right?
Yeah, current, and in the diffusive case, you have to know. I mean, yeah, of course, yeah, current, yeah, so that's current.
So in the ballistic case, what replaced I mean, in the usual DMFT, people indeed say, okay, I just need to know the diffusion constant. In your case, you just need to know the average of the ballistic current. Is it correct?
Sure. A. Yeah, that's perfectly correct. All you need to know is A. I mean, essentially, all you have to know is hydrodynamics of it. So, which means in the Euler scale, at least in integral systems, the information about A.
Okay, but can you check if this is if all these assumptions that you do are actually correct, and indeed like because you could also derive these cumulants macroscopically, no, and check if DMFT give the correct result.
Yeah, I mean that's what I did just now. So, for example, in the well, microscopically, I don't know.
Okay.
I'm not sure if this. Yeah. I don't know if I can call this ballistic fluctuation theory, for example, microscopic. But in principle, you can do it. But I'd say there's no form factor result, for example, for the even for the second increment, I guess. So yeah, in that sense, the comparison with the microscopic computation is still absent.
Okay, and finally, can you say anything about the distribution, or you can only compute cumulants, but okay, you cannot reconstruct the full distribution?
You mean the probability distribution?
Yes.
Oh, I mean, why not? If you have these cumulants. Okay, yeah, there's one thing. So indeed, we still haven't succeeded to compute the full scaled cumulant generating function from within the MFT. This was, by the way, done within the framework of BFT and ballistic fluctuation theory. So if you do that, then you can do the Legendre transform and get the probability distribution, right? But yes, in the MFT, it's still missing to compute the FM lambda essentially, and for now, I'm not sure how to do it.
Okay, thank you.
No worries.
Okay, next, Ohad.
Okay, thanks. Hi, Takato. So let me try to understand the regime of validity here. So for example, for TASEP, the full cumulant generating function is known for on the ring. There is a paper by Derrida in the late 90s. Is it going to work on a ring or just on the 1D infinite chain?
Yeah, I mean, they are basically supposed to be equivalent because I'm taking thermodynamic limit and imposing the periodic boundary condition to get the beta equation essentially, and TBA. So I'm not really distinguishing these two results.
Okay. Did you compare the two?
Not really, because I'm taking really thermodynamic limit, and I mean, so yeah, boundary condition and periodic boundary condition imposed already. So I'm not concerned, for example, open infinite chain case that I haven't done that.
Sorry, Takato. May I make a comment here?
Yeah, sure.
Oh yeah. So yeah. So for TASEP, there have been several large deviation results, as you know. And for the periodic ring, as I said, there is a paper by Derrida, Leibovitz, and so on. But for the moment, what we are considering is basically infinite case, right? So for Derrida case, so they consider the first a large T limit and then take large L limit, right? But this is not what we are thinking now. In our case, for the moment, for the moment we are thinking the infinite line and consider large T large deviation, right? And
so
also
also
for this case, they're having several works based on exact solutions and so on. And for example, so TASEP is known to be related to random matrix theory, so Laguerre ensemble. And by using such a Fredholm determinant and so on, so one can also study large deviations. So these kind of results can be reproduced by our scheme. This is something we have checked. And also, as Takato also pointed out, so large deviation for TASEP is also formulated by Jensen and Varada. And they also found, for a particular case, the large deviation function. And this is also comparable to, can be reproduced by our methods.
Okay, so what I was trying to understand, you see, in the macroscopic fluctuation theory, you can consider various boundary conditions. You can be on a ring, in an infinite chain, on a boundary-driven case. It always works. So here, is there a reason why it wouldn't work on a ring?
No. So we are hoping,
because this is the simplest case.
Depends,
because you have exact results for any lattice size and any occupancy.
I mean, this is essentially a ring, no? I mean, the case I'm considering is essentially ring. I mean, infinitely large ring, right?
I think it depends how you take the limits. But okay.
Taking how to take the limit,
yes,
how to take limit. That's
this
important.
is an issue. Yes. Okay,
so the formulation should work also for finite ring and so on. But yeah. So for the moment we are sticking to infinite,
because I think this is a very easy check to see if your results agree with their results.
Can I just add one thing? So on the infinite line for TASEP, I mean, it was verified by my student Jason Myers in his thesis that the ballistic fluctuation theory, which agrees with this, actually reproduces the TASEP result. So that agrees with TASEP on the infinite line.
Yeah, I see that you have checked for the infinite line, but I'm wondering, okay, it worked for in simpler case, the ring. I think it's worth checking.
Yeah, I mean, I'm sure it's not too difficult to do, at least in a TASEP case from our equations. So it's a good idea. We should check.
Okay, so what about the asymmetric exclusion process? Is it going to be very different?
Yeah, I think it was. I don't know if actually people managed to really successfully apply MFT to the ASAP case. Maybe Tomohiro knows more.
Yeah, what do you mean? The asymmetric simple exclusion process is basically diffusive, right?
Well, if it's weakly asymmetric, right?
Okay.
Only if it's weakly. If it's not weakly, then it's ballistic, and then it should be, I guess, within the regime of this theory.
Well, yes, since such ASAP has the same hydrodynamics as implicit Borg equation, we are just thinking that it should be the same, right?
Because I think that the ASAP is a bit more interesting. There are possibilities of dynamical phase transitions.
I see. Also for large deviation function. You're saying that
so you see on a ring for the weakly asymmetric exclusion process, there is a dynamical phase transition, and I would be surprised if there is something like that doesn't occur also in ASAP. But okay, I don't.
Yeah, thank you. Yeah,
I think it would be interesting to explore. This is okay. It's a harder model, but it's richer.
Yeah.
Okay, so maybe one last question, if time allows.
Okay, sure. Yes.
Okay, so the big idea in the fluctuation theory is that if we know D and sigma, we basically know everything, right? Up to hard calculations, right? So in principle, there could be two very different microscopic processes that lead to the same D and sigma that would give us the same result in the hydrodynamic limit. So we throw away a lot of. So here, this is the same. So everything we have to know is just the currents and the conserved quantities. And so would it work for models that are, just slightly non-integrable? So if we take an integrable model,
interesting question.
We put some dial, change it a bit. So now, integrability is easily lost. Would we get something close?
Yeah, so firstly, in the integrable case, it's really universal because essentially the mechanism of GHD is, universal. It's same for all the integrable systems. So in that sense, I don't expect any difference of the MFT behavior. So long as it's a ballistic transport. Of course, if you consider, for example, the spin transport in the gap regime next to spin chain, it's very diffusive, so it's a slightly different case. And if you go to isotopic, it's KPG, it's even more different, but still. If you put integrability break-in, then things could be totally different. And as Jacob was talking, the first state it basically makes it just a usual few component. The system with a few conservation loads. So that would be still described by MFT, but to calculate the necessary input for the MFT to work, like a transport coefficient, all these might be a bit difficult if you break integrability. I mean, yeah.
Okay, thank you.
So also it's time. Time is also already up, but Kranik, you have questions? Yes,
Yeah,
you can ask.
A very basic question, but here you introduce the time integrated current and then rescale it as 1/t. And then for if the model is ballistic, this will be of order 1. But in a different model, this will fall off as 1/√t. But then could you somehow adapt the framework to also access the fluctuations on this 1/t time scale?
So the time integrated current scale is linear in T, right?
Not for diffusive process, right?
I mean, for a ballistic case, at least.
Yes.
So yeah, of course, there is a matter of scaling. I mean, you have to change the scaling property to see that they are scaling in T. But there are cases that are really tricky, like the current as well as the high cumulants are scaling like a square root of T. But yeah, again, if you do appropriate scalings, you can see that with appropriate scaling, I mean, under that scaling, you can see some non-trivial activation as well, I mean, within the framework of MFT. So you have to know the scaling of the system first and then try to.
Right, so if you know the scaling, you can basically adapt it to whatever scaling you like. Okay, thank you.
Since time is already up, I'd like to close this session. Let's thank Takato again for an exciting talk.